maybe we should start and we'll wait for more people to join eventually. So, good morning, everyone, and welcome to today's EPICURE webinar, From Theory to Practice, HPC Performance Analysis with Scorpi, Scalasca, and CUBE, which is the second of 5 sessions in our webinar series on profiling, designed to guide you step by step through the key concepts and tools of parallel performance engineering. We are delighted to welcome you and talk about profiling. So, our two speakers, one of them is Ilya Zukov, is a senior HPC consultant at the Jülich Supercomputing Center, with over 8 years of experience supporting users of large-scale HPC systems. He has been closely involved in the POP-CO, CIVGCS, and EPICURE projects at JSC, providing hands-on support to researchers across diverse scientific domains. His primary focus is on helping users exploit HPC systems efficiently and improve the performance and scalability of their applications. Our second speaker is Michael Knobloch. Hopefully I said the name well. Obtained his diploma in mathematics from TU Dresden in 2008. He joined Jülich Supercomputing Center at Jülich in 2009, where he works as HPC performance engineer ever since. His research interests include, but are not limited to, performance engineering, energy consumption, analysis of large-scale HPC systems, and applications and the development of corresponding tools. He's an active member of MPI Forum and regularly gives courses about parallel programming and performance analysis. Thank you, Ilya. Thank you, Michael. So maybe we can start with a webinar. Just a few notes. I'd like to inform you that you can and should interact during presentation, and to do so, you can use the chat to share your questions during the presentations. There are no discussion moments during the webinar itself, but in the end, the webinar will provide some minutes to discuss all the questions and interact directly with you. I'll be monitoring the chat activity regularly, ensuring that all questions are dealt with by the speakers at the right time. So if you have any question, just use the chat to put your question there. Thank you so much. Now we move to the presentation. Ilya and Michael, the screen is yours.
Thank you for a very nice introduction. I hope you can see my slides and can hear me. So if I don't hear back, so I assume it's right. So last week you learned about performance engineering in general, and today we'll provide a short intro about parallel performance analysis with Scorpi, Scalasca, and CUBE. And we'll provide a short demo how you can do it. Let me start with the history. So Scorpi was established quite some time ago. So it was established within Silk and Prima projects, European projects. Basically, idea behind was to develop a code which replaced tool-specific instrumentation and measurements components of other tools. So basically, there were multiple, you can imagine there were multiple tools, and each of the performance analysis tools has its own instrumenter and its own measurement system. And of course, to maintain it, it's require a lot of human work, a lot of and of course also a lot of digital noise appearing, like a lot of generated data and so on. So the idea of this project was to get together some partners and implement a single measurement system which can be recycled by different tools. Here I listed partners which were involved in this project. And I think Michael was at the very beginning of this project, and so it was from 2009 to 2011, where it was the first version of Scorpi was designed and implemented. So Scorpi you can find on this website. I hope you can see my cursor. So again, the idea to replace instrument and measurement system among different tools and provide it to tools like to recycle the measurement system. Let's briefly cover Scorpy functionality. It provides a typical functionality for performance tools. As we discussed last webinar, there are two ways of getting information about your execution of your application. One is instrumentation, where you insert a certain hooks in your source code. It is supported in the Scorpy with various methods. Sampling is also supported in the Scorpy, and Scorpy also supports different paradigms like MPI for multiprocessing, for threading it's OpenMP, POSIX, and others. Accelerator based paradigms like OpenACC, CUDA, OpenCL, ROCm, Cocos. And you can also combine as a combination. For example, you can combine MPI, OpenMP, and CUDA. Like I put almost, but for example, not like every possible combination is covered, but most of them is possible to combine. And flexible measurements. Scorpy allows flexible measurement without recompilation. You did once, for example, you instrumented once your application, then you recycle it for in the multiple tools. And also create a different measurements with a single instrumentation run. And it allows to create a basic and advanced profile generation. Profile is generated in Cube4 format. And also it's possible to collect traces in OTF2 format. So I'll remind you from the last the webinar, what is the difference between profile and trace. So basically in profile, you see the aggregation statistics about execution of your application, whereas in the trace, you see the chronology, basically the life of your application with many, many more details. And Scorpy is highly scalable and supports all fundamental concepts of partner tools. Like partner tools, I will cover on the couple of slides. Then what are the advanced features of Scorpy? Measurement can be extensively configured via environment variables. So basically, in your bash script, you put a multiple environment variables where you can set how your applications should be measured. Do you want to enable CUDA? Do you want to CUDA measurement, or do you want to enable filtering file? Everything can be set via environmental variables. And it allows also to fine-tune your measurement. For example, you can also select what you want to record. Not everything. Maybe you're only interested in initialization phase or only in the scientific loop. This is like it's called selective recording. You can also switch on and switch off recording when it's necessary or unnecessary. Then you can also record the special phases, for example, init, finalize, special foo function, and it will be also recorded in a special subtree. Also possible to create a parameter-based profiling. For example, depending on the, you have a function foo, and depending on the input parameter p, it changes behavior or like has a different runtimes. But you can also enable it and get the profiling based on the parameter. It will be also stored as a separate subtree. Then it's so very important that nowadays GPU support is ongoing, and it's always improves. It's at the moment CUDA, OpenACC, OpenCL, HEAP, Cocos is supported, and more is coming. Please ask us or see the user manual for details, because I only highlighted some options what I allowed in the Scorpy. Now let's talk a little bit about Scorpio architecture. Don't worry, it's not so complicated as it looks on these slides. So in the green, you can see your source code, the green rectangle. This is your application. And also this green rectangles inside, this is your paradigms what you use. For example, MPI, OpenMP, CUDA, or something else. And then you would like to instrument your application or enable sampling. You can enable sampling, or you can use an instrumentation wrapper to enable Scorpio measurement infrastructure. And you basically enable through the wrapper. There are different ways how to do this, but basically you run after instrumentation, you run your application, and then at the end there are two ways how you can get data. First one, you get a profile in the Cube4 format, and you can read these profiles in the different tools. This is like listed tools which are supported. We are covering only Cube in our talk. And you can also enable tracing. Tracing is collected in OTF2 profile trace format, and the traces can be visualized or analyzed with Vampire and Scalasca tool. So in our talk, we'll cover Scalasca tool. Scalasca also allows to generate enhanced Cube4 file and also analyze it with, for example, with Cube on all other tools. This is basically how Scorpio architecture works. Now let's talk a little bit more about Scorpio tool ecosystem. On the left, we see our application instrumented with the Scorpio, where you might enable hardware counters or just instrument it. And then you have again multiple ways how you work with multiple tools. So first pass, if you collect a simple profile, which is generated, as I already mentioned, in Cube4 format, and this file can be visualized with a cube, which we'll also cover in our talk, or it can also be visualized with Tau. And there are other tools like Tau, Perfect Explorer, and XtraP. This is useful tools if you have a series of measurements and you want to do like analysis how this function will behave if you scale up. Or Tau Perfect Explorer, you can also data mine Cube4 files and maybe understand more about measurements. Another way is depicted below. When you collect traces, traces can be analyzed in parallel with the Scalasca, and after the analysis, it also generates a Cube4 enhanced Cube4 report, which can be again visualized with Tau or the Cube. And there is also other way you can just simply visualize your traces with a Vampire. Vampire and Cube can be also interconnected via CV instances, for example, where you can from Cube specific metric jump to a specific point in time in Vampire. Quite a handy option. Now let's talk about Scalasca, because in our demo we will use Scalasca plus Scorpio, Scalasca, and Cube. Basically, Scalasca stands for Scalable Analysis of Large Scale Application, and the approach is the following. You instrument your application, which is written in C, C++, on Fortran, with the Scorpio. You enable measurement, and you do the usually start with the profiling. This is my part of the talk. I will consider the Cube profile created with Scorpio and Scalasca and examined in the Cube. And option 2, or a little bit more advanced, once you already done option 2, it's a scalable event trace analysis. So basically you collect the traces and process traces in parallel, identifying a special weight state analysis, delay and critical path analysis. This will be covered by Mikhail. And of course, after that, it's categorized and can be visualized in the cube. This is the scheme how it works. But Mikhail is gonna cover a little bit more about this. So basically, you take your source code, instrument it, execute it, collect the traces, do the analysis in parallel, and after identify some wait states and create additional report, which can be visualized in the cube. How cube is working and what is the cube, I will discuss later in the demo. What is the typical performance analysis procedure? So basically, we already discussed it last week, but you have to identify, do you have a performance problem at all? So basically, you can identify it by measuring the time, creating speed up or efficiency plots, do the scalability measurements, and see the efficiency and scalability, speed up if it's ideal or far away from ideal, then you might get a problem. Then, of course, first question would be, what is the key bottleneck? Is it computation or is it communication? Here you can probably start with a flat profile and see how much time you spent in MPI and OpenMP, and also check what's the proportion between computation and communication. If more time is communication, you obviously have some communication issue. Then once you identify what is the bottleneck, you want to identify where it's in the source code, then call path profiling is your friend, and you can identify in which function it's happened, and then you can try to optimize this particular function. So basically, in my part of the talk, I will concentrate what and where it will be combined. So we'll skip flat profiling and dive in immediately to the call path profiling. Then Michael is going to talk about why is it there, and basically there Scalasca trace analysis is particularly handy because it identifies inefficient communication patterns, critical paths, and delay analysis. It provides also very detailed delay analysis. And of course, you have to see if your code has a scalability issues, then you have might need to do the load imbalance analysis and compare profiles at the different scales and compare function by function. So first two steps, I'll combine it. What and where is the key bottlenecks? For this, we will generate a call path profile using SCORP and Scalasca, which requires recompilation. Then we will use runtime. So basically, we recompile our application, rerun our application, and see how much it takes before and after using instrumentation. And if the overhead is too high, then you have to exclude some function from the measurement. And so basically, we'll recommend to start with option one, where you use the automatic compiler-based instrumentation. Basically, you use compiler options to instrument your application. But you can also use in-depth analysis where you know exactly what you want to look at, where you can insert manual instrumentation in interesting phases, routines, or loops. Now let's briefly talk about call path profile, and here's a recipe. You will first start with the reference run and know the runtime. You prefix your compile and link commands with the SCORP. So basically, before MPI CC, let's say, if you have, you put SCORP and recompile and relink your application, then you run your application with the prefix Scalasca -analyze, and after execution, it creates a measurement. And you compare this measurement runtime with step 0 without instrumentation. And if it's significantly, so identify the overhead And if its overhead is too high, you might need to analyze what might be necessary to exclude from the measurements. This can be done with a so-called scoring. And in this scoring, you can identify what can be excluded. Potential candidates for exclusion is tiny functions, which are, let's say, if you have a C++ function, it's get, put, set functions, which are very, very tiny, but overhead caused by the measurements is significant in these cases. Then you can prepare a filter file automatically or manually. Here's example how you can prepare your file, Scorpio filtering file automatically with Scorpio score -g option, and then provide the path to your profile.cubex, and then the filtering file will be generated automatically. And you can fine-tune this generation. Here is the example of the filtering file. In the filtering file, you can have a multiple blocks where you can exclude and include certain files and also regions. Like, for example, here we decided to exclude everything, every function, but only include this for functions. And you can also use asterisk, white, and so basically question marks and asterisks are possible here. And once you prepared your filtering file, you have to apply it and rerun Scalasca analysis with -f option and pass to the filtering file again. And after that, you can examine results of the execution. Here's a typical results with the 3 metrics, 3 panes. This is a cube. They have 3 panes. They are all coupled. In the first pane, you'll see what kind of performance metric, like time, where here you'll see the source code, where exactly the source code is happening. And here on the last pane, how this specific metric is distributed across processes threads. And for our case study, we'll use a Cloverleaf OpenACC. This is a mini app implemented by UK Mini App Consortium. It solves the compressible Euler equation in 2D. It's open source. You can download it and run it. And in this case, we will use OpenACC MPI version, but there are other versions with the CUDA, HEAP, and other. Please explore, and there are also different test cases which you can test. In our case, we'll use 87 timestamps and this certain amount of cells. And with the demo, I hope Jupyter allows us to do this. So we will run on 2 nodes of Jupyter with 4 MPI per node. Per task per node. So each task has at least one GPU. Now let's start with the demo. Yeah, let me. So I hope you can see the screen and it's readable. Unless if it's too small, I can make it bigger. So basically, this is our source code. And first, as I already mentioned, we have to do the reference run. So we have a make file. We can open the make file, and you'll see all the function, all the settings are here. In this case, we are using PGI compilers. Everything is already loaded. So basically, I loaded NVHPC compiler and OpenMPI. So I can load them again. So I use NVHPC, OpenMPI, and I already loading Scalasca. Yeah, it's loaded. Then I can make. So basically, what you can see here that typical compilation process and linking process. So we have MPICC and our source code. So it's done. So let's go to the bin directory where executable is located, and we have the following batch script where we have 2 nodes and 4 tasks per node. So here we again load our software, and we run our application as usual. Yeah. So if I submitted it, so basically it is let's see. It is already running. It is running about 40 seconds on 2 nodes. Let's wait a little bit more. So basically it is running and it's executed 87 iterations. And we just need a runtime for the solver loop. Okay, so it's finished. We have output. So basically, if we open it, we will see that we have 8 tasks and multiple steps. In this case, it should be 87. Yeah, 87 steps. And we are interested in the wall clock. This is only about solver. The rest is initialization. So we have almost 7 seconds in the reference round. Now we need to instrument our application. For this, we go to our make file, and we basically put prefix like this. So we'll use scorp for instrumentation, and here we also need to enable OpenACC, CUDA, and user. But in general, if you start with the application which is MPI only, so you don't need to put this, but it's highly dependent on your application. So basically, this is enables OpenACC adapter, this enables CUDA adapter, and this enables user instrumentation, manual instrumentation. Okay, so we enabled. Let's do make clean and make again. And now you can see the compilation is a little bit different. So we have a prefix before MPI F90. We have a special prefix, and okay, we are done. So let's go to the bin.scorp directory. It stores in a different directory because we don't want to mix different executable. It is already there. So, and then we'll open a batch file for the Scorp. Then basically we need to before we were running srun dot dash cloverleaf, but now we have to prefix it with a Scalasca dash analyze -t. We don't need at the moment. So what we need is this. We can also manage our execution with the different variables. So for this, we would need OpenACC. We would need CUDA. This we don't need. This would be necessary for tracing. We also don't need. Let's exclude. We can also set the variable of the name of the directory of the measurement directory, but default will be created by Scalasca. So basically, we would need only to enable OpenACC and CUDA to enable measurement of the certain adapters, of the certain parallel paradigms. But in principle, in a simple case, you don't need to set any variables. You just put Scalasca dash analyze and before your srun as it's it, and you can run it. let's see. So it's already running. And before, as you remember, it was roughly 40 seconds. Now it depends on the overhead. So, so because we use a measurement, Scorpio measurement, and this can induce some overhead. Yeah. Um, what you also need to know is that the directory name by default won't be overwritten if you use Scalasca. So basically, you need to rename your measurement if you do it next next time. So basically, now we have a measurement. Let's check the output. So we see where also timers automatically added by Scalasca. We have steps. And we also have a wall clock time. It's roughly the same. It's a little bit slower. It's 7 seconds, but basically in this case, we don't need filtering file at all. So this is fine for now. And also we have some additional information about profiling, so the runtime and so on. And also the directory created by Scalasca has a meaningful name, and we don't need to rename it. But as I said, if you want to run it again, you would need to rename it or change the directory by environmental variable. So, but in this case, we don't need scoring at all. We don't need filtering file, but I'll briefly show scoring, how you can estimate which functions are useful, which are not. So basically what you're doing, you can do Scalasca. I can show a shortcut for Scorpio score. And then we'll provide a path to the profile. And then you'll see the summary of your execution. So this is useful, this Scorpio total memory. This will be needed if you would like to collect the traces. In this case, it's quite small, 17 megabytes, but in many cases, it will be much bigger. And here you can also see the summary. You will see summary about different types of the calls you have. For example, CUDA calls, OpenACC, COM, it's combined. For example, inside your foo function, you have an MPI call. This type of function is called combined. Obviously, we have an MPI runs, user functions, pure user function, and also additional score P function, additional function. So, and here we can see max buffer, which is necessary for collecting information about the call. So this is information is necessary for tracing. Also, we can see how many times it was called, time in seconds. It's aggregated time across all call passes and processes, time in percentage, time per visit, and so on. But if you would like to see a little bit more information how it is distributed across function, then we will add -A or R option, and then we'll see the breakdown across multiple functions. Yeah, here we will see much more and see which function was like type of the function, max buffer for the tracing, how many times it was visited, time is in seconds aggregated, times in percentage, time per visit. And as we already mentioned, that the best candidate is the small, when you have a very tiny amount of time per visit, tiny calls. But of course, it's up to you what you would like to be filter or not. For the filtering, you use score P minus G option for generating the filter, like for automatic generation of the filter. You use this, and it creates the file. It by default it's called initial score P filter, but in this case it will be empty. But depending on the application, it might vary from time to time. Yeah. Okay. Now let's examine results. So we are fine at the moment, and then we can use Scalasca minus examine, and then we'll use okay, and it should open a GUI. I'll open it in the browser. Oops. Because on the Mac it's okay. So basically, what you should see, this is the on the this is a cube file. It's opened remotely. Usually you can copy your profiles and open it locally, or you can also open use it on open on demand, or in my case I use Xpra. You can also use client server. It's up to you what you use, and depending on your bandwidth there are different options. So now very briefly about cube. So we have 3 panes here. So we have a pane with a metric, different metrics and different hierarchy. So, and here we have a time, visits, and so on. And they also have a sub hierarchy like execution, overhead, time and GPUs, time in here we can already start to analyze our application. So we see that 95 seconds is in computation, 25 in MPI, and 71 is in CUDA on CPU. So basically we can already see that we quite good in computation. We use computation is intensively. It's not like the most time we are spending in MPI, but also it's quite significant time in MPI, and it must worth to look into the communication part. Then the second pane is the call tree. So here you can see the call tree. Basically, with here we can see what's going on on the CPU part, on the GPU part, and we can also see the relation. So we can basically see that inside initialize we have a multiple function. We can open them and see the breakdown on the function. You always read the cube from left to right, but the values are aggregated from right to left. So this is like you have to play a little bit with the cube to understand and to get used to it. Here is a call tree. There are a lot of information. Here we also have a part which is executed on the CPU, and this is like kernels on the GPU. We can also indicate the time because it's time selected here, and all the panes are coupled, so time. And we can see also additional metric which shows when the GPUs were idling, which is quite useful. And on the last pane, we can see the distribution of on the system tree. So as you remember, we had 2 nodes. Yeah, let's collapse everything. So we have 2 nodes on Jupyter, and inside Jupyter we have 4 MPI ranks and 4 CUDA devices. So yeah, as I said, values aggregated from right to left, but you should always read from left to right. So so at the moment we see, let's open like this computation time in the function initialize, and here you can see the breakdown of MPI of runtime of compute time in initialize function across MPI ranks. Yeah. And sometimes, like here, we have like just 8 MPI ranks. It might be not very interesting, but quite handy is to check statistics about this. So basically, you can see max time across all across these values, a mean time, and also mean and statistics about the run. So it's quite handy. Also, colors indicated that blue is quite low value and red is big value, also bigger value. All right, I think I'm almost out of time but basically this is idea how you identify what kind of issue you have. Probably you should look here into the communication, and you can also identify where in the source code here computation is mostly initialized. Maybe you would like to look in the initialize. So basically you identify what and where. If you want to look an MPI problem, you will see that most time in MPI are spent in these two functions. And then you can break down and see exactly, for example, here significant time is spent MPI init because it's a CUDE MPI and it requires some additional bookkeeping to keep everything and to for CUDA. That is also you can also find mapping between OpenACC and CUDA calls. Here's what is executed on the GPUs, and for example, if you click here, you will see where it is what invoked on the CPU part. So basically, you can map CPU and GPU part in this. All right, I think I covered basics. If you need more information, you would need to attend one of our additional courses. But let me stop sharing and Mikhail can continue.
Can you see my screen?
Yes, we can.
Perfect. So you can see the slides, hopefully. Present a slideshow. Okay, so Ilya covered basically how to get an overview of how to find the bottleneck in your application using a profile, right? You see how much time was spent in user code, how much time was spent in communication, how much time was spent in your GPU kernels. But now the question arises is, if you find there is a bottleneck, why is it there? And unfortunately, this is highly application dependent. So there is no golden rule to say this is there because of that reason. So you do typically need additional measurements to find out why a bottleneck that you found in profiling is actually there. For that, you have multiple ways to do further analysis. Right. So if you see, okay, you spend a lot of time in computation, in user code, right? This is typically what you want. What you want to know, is that efficient enough? Right? Do I use the hardware resources efficiently? So what you can do there is you do a hardware counter analysis, right? So hardware counters are originally developed for CPU debugging purposes. So the CPU basically counts what it does internally. And some clever guys came to the conclusion, hey, we can use that for performance analysis to check what was done on the hardware that we used and whether we used that efficiently. There are a couple of ways to obtain hardware counter information. The most widely used one in HPC is through PAPI, but there are other ways like perf, the native interface provided by the kernels since 2012, I guess. There's also a tool called Liquid developed at Erlangen University, which gives a nice interface to hardware counters. We support most of these ways in Score P to obtain this information. And then you can use it to basically get the CPU utilization, to check for the cache behavior. So you can basically count the cycles you waited for memories, or the number of cache misses, and so on. So there are a lot of interesting things you can get from hardware counters. Unfortunately, this requires at least some experience, because those things are not portable, right? So different CPUs offer different counters, and even from the same vendor in different generations, there are counters added and removed. So having a feeling on what counters you actually need to measure to get a reasonable results requires some experience. And then, of course, you can use selective instrumentation. So if your overhead is too high, as Ilya already mentioned, you need to get rid of that to focus on what you really want to see, right? So you have what we call in POP, and we will talk about that in the next iteration of this webinar, is a focus of analysis, right? So this is the section that we really want to look into in detail to see what's going on, because this is where we potentially can get the most of performance. And of course, if you see that you have issues in communication and load balancing, you can do an automatic or manual event trace analysis. And this is what I'm going to talk about now, because we have tools for that, especially for the automatic trace analysis. So this is where Scalasca comes into play. Right? What we found in many applications in the past, and this is a development going on for decades now, right, is load balancing issues that result in the same patterns in the analysis result, right? And the idea was then that we can automatically search for these patterns of inefficient behavior, and then we can classify that, and we can quantify the significance of each of these patterns that we found. So we tell you what happened, what went wrong in the application, and we tell you how much influence it had on your total runtime. Right? But this is nice to have, because we can see some inefficiencies, but Scalasca is also able to tell you the root cause of these inefficiencies. And I'll show you in a minute how we do that. And the nice thing of Scalasca is, as I said, it's an automatic trace analysis. So we take the whole low-level event trace data, which can be gigabytes, even terabytes of data, depending on the scale of your run. Right? Then we do a parallel analysis and only give you a high-level result back. And this is in the same format as a profile report that you're used to with CUBE. So you looked at the profile, you say, okay, here I have an issue in my communication. You do a Scalasca analysis, and you get an analysis report in the same format as a profile report. So you basically don't have to learn another tool. You just use the CUBE GUI and look at the Scalasca trace report. And why is that nice? Because we are guaranteed to cover the entire event trace. So all the hundreds of gigabytes of data are covered in the Scalasca trace analysis and shown to you. And this can be way quicker than a purely manual or visual trace analysis. And how do we do that? Well, we do a parallel replay analysis that exploits the available memory and the processors to deliver scalability. So basically, we use the same resources that were used to do the computation, the calculation of your application, and run the trace analysis after that on with the same resources. So, and what are these patterns that we are looking for? Well, we call them MPI weight states, basically. So looking at the first example here, this is what we call a late sender. So we have two processes, A and B. One process sends a message to the other process, right? But the receiver posted the receive before the sender was reached the MPI send, right? So it had to wait for the sender to arrive at that point to be able to send the message. So as I said, we replay the message, so the sender here knows its timestamp when it entered the send, and instead of sending the original application data, in the replay it sends its timestamp, right? And it's a point here, the receiver receives the timestamp of the send and can calculate the difference between its entry point to the receive call and the entry point of the sender, and can calculate its waiting time. So far, but this also works the other way around. But how do we do that? Well, we do multiple passes, right? We do a forward replay and then a backwards replay. In the backwards replay, we reverse the direction of communication. So in the backwards replay, the second pass, the original receiver sends message to the original sender with its timestamp. So in the backwards replay, the sending process can calculate what we call a late receiver timestamp. Right. So those are the point-to-point patterns. Basically, we can do it a bit more complicated. So we can look for messages that are sent in the wrong order, where we could actually save some time by sending messages in a different order. But this also works for collective communication. So for example, here at an N-by-N collective, where every process or all the processes synchronize, the process that enters that collective last basically determines the wait time for all the other processes. Right, so in this case here, this guy enters last, so all the others had to wait for a certain amount of time. Right, again, here we send all the timestamps, and each process then can calculate their respective waiting times. And as we mentioned last week, we have task local trace files. So we don't have a global view. So we need this replay because there is no single global instance where we can just look this information up, right? Because data is way too big to be stored on a single process usually. So that's why we need this parallel replay. Okay, so as I said, we are not only show you the wait states, but only where they come from. And for that, we do a root cause analysis. The approach here is we categorize wait states by direct and indirect wait states. So direct wait states are caused by an imbalance early in the program, and indirect wait states are caused by a previous wait state that was observed. Right, looking at the example here, A sends a message to B. There's some imbalance here, so B had to wait. This is a direct wait state. And then C had to wait for a message from B. So it has to wait for a longer time. So there is some time that is just caused by the work on B, and some time that is caused by the wait state we discovered before. So we see how wait states propagate through the program, but we are also able to basically go back in time and say the root cause for this is actually the imbalance in the routine foo. So this has nothing to do with the bar. This bar here is perfectly balanced, but the root cause for this wait state is the imbalance in the foo routine, and that's what we call delay. So this is basically what you're looking for, these delay metrics, and try to balance this routine across the processes, because that gets rid of this initial wait state. You will still, even if a perfectly balanced foo, you will still have some wait state here, which is simply caused by this sequential sending of messages. Right? So you won't get rid of every wait state in your programs. It's simply impossible. But we tell you basically where you can do something in order to improve the performance. And another thing that we show you is basically the critical path of your application. So this is the longest runtime between two synchronization points. Because this is basically the path that determines the runtime, the overall runtime of your application. Right? So even if you would improve that routine here by a factor of 2, you just would wait longer, right? Because the critical path is on these processes. So this routine here is not on the critical path. So improving performance of that has no influence on the total runtime. Right? So you should focus on the things on the critical path for tuning. Of course, once you tune your routines on the critical path can change. Right? So tuning potential then shows up on other functions. But this is what you should focus your tuning efforts on. Right, so what Scalasca does, it generates a cube report with additional metrics. Let me show you a quick demo on how to do that. Ilya already showed you how to run the application with Scalasca. It's just adding the -t option. So this basically tells Score P to not only generate a profile, but also generate the traces in OTF2 format and subsequently run the trace analysis after your job ran. Be careful, these traces can quickly become extremely large. So please do a profile first, do your scoring, filter accordingly that you get a reasonable trace size and that Score P total memory to whatever the score report told you to avoid intermediate buffer flushes. Because as I said, we are looking for these patterns of weight states, right? And if you have unsynchronized buffer flushes in between, you shift all weight states that come later on, right? If you had a buffer flush here, you would basically move the center later in time, so you would basically get rid of this late receiver. So avoid buffer flushes at all costs if you do a Scalasca analysis, because you basically can throw away your report afterwards. So remember to use proper filtering, selective instrumentation, and the Score P memory specification in order to get a reasonable trace analysis. Okay, let me show you a quick demo so you can see my terminal, I hope. So we have already created a couple of measurements. As I said, I don't go into details, but I have to mention something which is really a pain in the ass right now for many systems that we have out there. The automatic trace analysis with Scalasca doesn't support GPU codes. So in order to do a trace analysis, you need to rerun your trace experiment without GPU support. That's relatively easy, as Ilya already showed you. You just have to set Score P CUDA enable to no, and you get all the host site information, and then you can do the trace analysis. Okay, so let's have a look at that thing here. So I have my local installation of Cube, so I'm not reliant on an XPRA as Ilya did. So we provide the Cube GUI for Windows, Mac, and Linux. So you can just install it locally. It's open source, so that's not a problem. Basically, both or all the tools, Scalasca, Score P, and Cube are open source, so you can install it anywhere you want. Vampire that Ilya already mentioned, which is a nice complement to Scalasca, unfortunately is a commercial software. So if it's available on your system, you're lucky and you can use it. It's a quite powerful tool. Unfortunately, it's not available on all your HPC supercomputers. Okay, as I said, we got some additional metrics in generated by Scalasca. The overall profile report looks the same as we had before, right? So we have our time, we have our execution time, we have computation, we have MPI time, we have management time. And this, unfortunately, is not a real good use case because it's way too fast. So the management time, especially MPI in it, is quite substantial compared to the rest of the MPI time. You won't see that in a regular application. Let's look at a communication point-to-point time. And now here we see we can split the MPI point-to-point time and see our late sender and late receiver patterns, right? So now we can just expand the subtree to the largest instance of this late sender pattern, and we see it's here in the MPI weight, all in the Clever module, Clever Exchange, in the Halo, in the initialization. Right? Again, we can look at the distribution over the system tree, as I already showed you on our two Jupyter nodes. And now, as I said, we don't have GPU information, so we don't see our CUDA devices here, right? We only have MPI, or our MPI processes. And here we see we have one process that didn't have to wait at all, though those were the one without any wait time. Right. So we can also, if you don't remember what these patterns are, you can basically look at the documentation. So you just right click and open the documentation, and then you get a description of the different patterns with the graphical representation. There is some diagnosis where you basically tell you what's happening and some ways you can try to mitigate the problem a bit. Right. As I said, there are the metrics for the delay costs, and here we see basically what for the MPI for the late sender time, what's causing the late sender time, and basically the module pack write is responsible. So the imbalance in the Clever module, Clever pack write, is responsible for most of the late sender times, or a significant time portion of the late sender times. Right. We get these wait states for, as I said, for not only point-to-point, but also for collectives. We have some patterns for OpenMP as well. So there's a lot of information that you can get from Scalasca if you want. If I have 5 more minutes, I can show you hardware counter analysis in shortly. It's up to you. I don't mind. Let's have a look at that. If we have hardware counters, we just look at the profile here. As Ilya showed you already in the job script how to obtain hardware counters. So it's basically, let me quickly get this. You just set an environment variable, in this case, scopy metric papi, with whatever papi counters you want to measure. In this case, it's papi.int, the total instructions, papi.cyc, the total cycles, and papi resource stalls. So the number of cycles you waited for resources to become available, right? And those things simply show up as additional metrics in the metric tree. So here we see, and again, we can just simply click through our metric tree to find the hotspots where the routine with the most instructions issued, which might or might not be interesting. As I said, these metrics alone don't tell us. So what we want to have are derived metrics. So for example, we want to have the instructions per cycle, and we can easily get that. So we can create a new metric in CUBE. So we just say create metric. We want to have post-derived metrics, and we want to have the IPCs, the instructions per cycle. IPC, so we have to give it a unique name. And we calculate it as a metric, papi.int, the total instructions by this calculation is done with a CUBE internal programming language called QPL, which is quite powerful. So you can basically create any additional metrics that you're interested in. And this again then shows up in your metric tree. So this is a metric we just created, and we can see the instructions per cycle that were issued in different routines. Right? So here again, you need some processor knowledge to see whether this value is actually good or not. So you can typically say half an instructions per cycle is not good. 4 is, I guess, quite good on an Grace Hopper super chip. But again, we just tell you what's there. You need to make sense out of that, really, and you should focus this analysis on the compute-intensive parts. But if you see here, okay, here we have a low IPC rate, we should do something that's typically not worth it. So looking at the time, we basically don't spend any time here, so we don't care about that at all. Right. Okay, and with that, I guess we are basically through. So as a short recap, So performance tools can provide very, very detailed insight into the application behavior. And they help you to identify bottlenecks and tuning potential. However, generating data is easy. Getting a good measurement that you can actually use to derive tuning actions from is not. So this requires some care setting up. So just firing up a profiler and hope it gives you all the data that you need is typically not working. It might in very special circumstances, but this is generally not possible. So think about what you want to record at which granularity, and take care setting up a measurement environment that actually gives you all the information that you need at a reasonable overhead, right? And of course, the last point, which is essential to this whole webinar series, talk to us. We are happy to assist you in your performance analysis endeavors, right? There are experts at all these centers that are happy to help you. And with that, we take questions.
Okay, thank you so much, Ilya and Michael. It was really interesting to actually know a bit more about Scalasca, Scorpi, and CUBE. For a person that actually hasn't been able to use any of those tools, it was really interesting. And I think we have one question by Benek. And he asked, is there CUDA support for Python-based applications in Scorpi?
Yes. So we probably should update the slides. There is CUDA Python support, which is unfortunately not in the traditional Scorpi way, as Ilya showed, where we have all the adapters for the different paradigms. CUDA Python support, is provided as an pip extension, so you can look at GitHub for the Scorpi Python bindings. You can install them, and then you can analyze Python codes as well. And then the same approach is true. So all these adapters basically are independent of each other and work for all these paradigms. So you can do any combination you like. So CUDA Python is no problem. MPI Python is no problem. Once you have the Python running. There are a couple of papers and the documentation you should look at to get a reasonable Python measurement, because overhead can be substantial in Python. Because you get a lot of these Python internal things that you are not interested in. So setting up good Python measurement takes some time, but it's certainly possible.
Okay, that's interesting. Actually, I have one question for each of the topics, and one that is more on my side on the AI part and things on HPC. So for Scorpi, actually, and are there specific information that typically us as developers overlook, but actually Scorpi can pinpoint and highlight such bottlenecks? For instance, at thread level or processes and stuff like that?
Typically, all these wait states is something that you basically don't have a feeling for, right? So you try to balance your work, but how it's balanced is hard to tell from just looking at the code. Right. So Scorpi tells you in detail. So this is what we really focused on. So there are better tools, let's say, for detailed GPU kernel analysis, for example. So basically NVIDIA Inside Compute, you can't beat that. There are profilers that tell you a lot on the system level for CPU activity. Better than Scorpi can. I mean, Scorpi can tell you a lot already if you collect the right hardware counters. But this is certainly not our main focus. So the main focus that we have is looking at load balancing issues. So that's where we spend basically most of our time. And this is something that you typically don't have when starting writing your application. So you basically start with a sequential application. You maybe tune that already on a single node or single core. So you have with whatever tool you use at that scale, have a feeling of how you use your resources at that point, and then you scale up, and then bottlenecks occur at scale, right? And we try to pinpoint those bottlenecks too.
Actually, and taking on that part of load balancing and scaling and stuff like that, I would actually like to ask, for instance, we are growing our HPC infrastructures, and so we are starting to have even more cores available to actually scale our applications. Have you seen some performance analysis challenges from using hundreds to thousands of cores and stuff like that?
Multiple. Right. So basically, we as a tools developer for large-scale tools face the same issues that application developers do in the end as well. Because in the end, it's a highly scalable application. And one of the main issues we found a long time ago with the Blue Gene P at that point, which is decades back, was indeed I/O. Something that we mentioned last time, that parallel I/O really matters. So we tried to open a couple of thousand files at the same time. And this took us a long time, way more than we originally expected at that point. Right? So this led to the development of a library called ScionLib, which basically maps these task local files into a few logical files, right, where you basically set your file view, so it maps this writing of task local files and opening of task local files into a few more general shared files, which increased the runtime a lot. So that was really an interesting point that we saw. And then getting load balancing right, it highly depends on the application, right? So if you have a tool, you have to maybe look at whatever mesh refinement methods or something like that. There is no general rule of thumb on how to get that right. Highly depends on the application.
And some of these bottlenecks can also be from misconfigurations on the MPE, MPI, and stuff like that, correctly?
Yes, especially on thread level, it can be NUMA issues. There can be MPI task placement issues, where you want to basically have processes that communicate a lot with each other. You want to place them as near together as possible to basically profit from a higher bandwidth, depending again on the network architecture. But if you have an all-to-all network, which you don't have, spoiler alert, then you don't need that. If you have a torus network like we had on the Blue Gene, task placement can have a significant impact. Again, depends on the machine, depends on the application. There is no general rule of thumb, but yes, it can have an influence, and especially in the OpenMP case, placement of threads definitely matters a lot. So you want to avoid false sharing, you want to avoid NUMA issues, so accessing remote memory is costly, for sure.
Yeah, let me chime in a little bit. So basically, we also see in our system with each new rollout of the software, like if new changes in the Slurm, the performances of multiple applications is changing because the settings of Slurm is changing, and benchmarking and profiling tools are helping a lot to identify what is the issues.
Yeah. It's really interesting. I actually had one question, but I think Michael actually answered it in the beginning. Scorpy, Scalasca, and CUBE can actually be joined with NVIDIA Insights and stuff like that to actually profile AI applications, right? You can actually take profit from both profiling tools and all of this information to actually have a bigger overview and bigger information regarding our applications. If I'm not mistaken, yeah.
With NVIDIA, it's a bit more difficult, right? Because they use a different infrastructure. Of course, you can use a profile to look at different things in these tracing-based tools. And so if you know what you're looking for, you can search in these tools to find these places. So we highly integrate CUBE with Vampire. So what Scalasca does for each of these patterns that it finds, it saves the worst instance that it found, and basically gives you the location and the timestamp, and you can open Vampire directly and zoom into that in that area where this instance was found. Right, so you basically don't have to look at the whole whatever X seconds of trace data where you don't see anything, but you can get a focused view. But this only works with Vampire because it's using the same trace data. That unfortunately doesn't work with any other tool. But of course, you can use profile information to get an idea of what to look for in other tools.
Yeah, that's I was actually thinking about, because we are trying to scale a lot of AI to a couple of nodes. There's MPI still involved in when actually doing the inter-node communication, but inside of the node itself and the links and stuff like that, it's a bit more difficult to actually use these tools. But for the MPI communication between all of the inter-node communication, that probably could be actually helpful.
Yeah, unfortunately for AI codes, it's a bit difficult when you get the information. That's not really the problem. The question is, what can you do with that information? Because you basically don't have any control of what TensorFlow or whatever PyTorch is doing, right? So you can try different alternatives and see whether they work better or not, but tuning these things is more difficult. I mean, PyTorch developers can, of course, use these tools to tune PyTorch to make more efficient use of resources, but as an end user of AI tools, it's a bit more complicated.
Yeah, exactly that. We had one question from Sari, but I think it's more if she can actually reach out to you for
we are happy
after this
to help. Right, as I said, send us an email, use the mailing list. So if you use Scalasca CUBE, whatever, there are mailing lists available where you not only reach us, but all the developers on all sides, and we are happy to assist you, right? So if there's a specific issue with one of the machines you're working on, write to your first level support. They assist you and reach out to us if necessary. But you can also contact us directly. Email addresses are mentioned on the slides. Send us an email, connect via LinkedIn, whatever. Reach out. We are happy to help.
Okay.
It might take longer if you don't use the channels, the official channels, let's say, because we all have a lot of work to do. So if you can use it via EPICURE, via POP, because we get usually paid out of these projects, right? And if we can just account the work we do on that, that's good for us. But we are certainly not limited to support on these projects, right? So whenever you run into issues, let us know, and we try to help you as best as we can.
And actually, you mentioned during the webinar that you have some courses that people can attend to learn even more about these tools and actually put a hands-on on their side. So,
exactly. So there are these HPS tuning workshops where we cover multiple tools usually, and it's a bring your own code workshop. So you bring your code, you get tool demos in the mornings with, I guess, 4 hours of talks, and in the afternoon, the tools that were presented in the morning are applied to the applicants, applications that they bring with them. Right? So we try to analyze all of these things and see what tool works best for specific applications, right? So not always, although we promote Scopy a lot, it's not always the best tool to use. But in these workshops, we present a lot of different tools, and you can find the tool that works best for you and your application. Ilya just posted the link to the tuning workshop series in the chat. And then again, if you don't want to make your hands dirty, you can apply for a POP audit if you're a European user where performance assessment is done as a service. So we do the hard stuff for you. There is a lot of information on the tools on the POP website with a lot of webinars, demos, blogs. So a lot of information is there if you want to get further information. There are a lot of resources on it. So for CUBE, there is a YouTube channel where a lot of the inner workings and usage of CUBE is explained by the main CUBE developer. So this is a lot of information to digest there. There's a lot out there. Just ask us. So that is. We can talk for hours about that topic without any problems.
That's nice. That's actually really nice. And if you're more interested, please just send us an email and we'll forward to both Ilya and Michael as well. So please get your hands dirty and reach out to us. So thank you once again, Ilya and Michael, and to all of you that still are here with us. And thank you for participation and your questions. And it's time to close this webinar. Thank you so much. And before we wrap up today's webinar, we'll also like to highlight the upcoming EPICURE webinar series. Actually, it's basically the next one, once again by Ilya and Michael, but it will be actually on another topic. You can once again register for these sessions, and please stay tuned to our communication channels for more information about these initiatives. So thank you again for joining us. Thank you, Ilya. Thank you, Michael, and I'll see you next week. Thank you so much.
Bye-bye.
Thank you. Bye-bye.
Bye. Thank you.
Bye.